Have you ever noticed that every elementary row operation can be undone? What do I mean by that? So we have some matrix A, and we apply an elementary row operation. Say we take a non-zero constant times a row of A, and store it in the same row. And this gives us our new matrix A prime. Now, using an elementary row operation, I can actually undo that change and go back to matrix A. In particular, since I multiplied row I by k, I could undo that by just dividing by row I by k. That would undo the elementary row operation, and it would go back, right? So I can invert the operation. Similarly, take a different matrix, apply elementary row operation where I just swap two rows. Say row I and row j. To get my new matrix B prime. Okay, I can go back to B using another elementary row operation. In fact, it'd be, in this case, the same elementary row operation. If I swap two rows, I can get back to where I was by just swapping them back. Okay? And finally, let's consider the third elementary row operation. This is multiply or adding a multiple of one row to another row. So let's say k times row I plus row j is my new row j. So that will give me some new matrix, call it C prime. I can go back to C by just subtracting off what I added. So negative KRI plus RJ to RJ. Okay? So in each case, every elementary row operation can be undone, can be inverted. All right? So what does this mean for elementary matrices? So let's say this corresponds to elementary matrix E1, and let's say this corresponds to elementary matrix E1 prime. Okay? So what this means is if I take matrix A and apply elementary matrix E1, that will get me to A prime, right? Then from A prime, if I apply elementary matrix E1 prime, that takes me back to my original matrix A. Okay? So what does that mean for E1 prime and E1? Well, since this holds for every matrix, this is true for every single matrix. In particular, it'd be true for the identity matrix. Okay? Which means, equating the left-hand side here with the right-hand side here, that E1 prime times E1 must be the identity. And that means that E1 prime with E1 must be inverses. Okay? So instead of calling this E1 prime, I could call this E1 inverse. Same thing here. These two elementary operations, they undo into each other. They invert each other. And so if this is E2, this must be E2 inverse. If this elementary operation is E3, then this must be the inverse of E3. Okay, so we notice a few things. First, every elementary row operation, or I'm sorry, elementary matrix, every elementary matrix is invertible. And second, the inverse of an elementary matrix is also an elementary matrix. Right? Because we just looked at all three elementary row operations. We know that using a different elementary row operation, we can invert them. We could undo them. And therefore, the elementary matrices corresponding to those inverse elementary row operations must be the inverse matrices of the original row operations. Okay? So, whoops. So this elementary matrix and this elementary matrix must be inverses. And this is an elementary matrix because it corresponds to an elementary row operation.